Hello everyone. Today, as you can check it out, the name itself suggests that our discussion topic will be periodic table. We all know about periodic table. We have studied many things, important parameters, the importance of the table. So, how the table looks like. We know that what are the different properties of the table, what, what are the major information this table provides. So, all these things we have discussed, or rather, I should say, all these things you all have studied so far. So, it is not very important right now to discuss all those the history of this table because that is known to you. In this lecture, we will be discussing something more, something else, based on what you have already studied, what information you are having regarding periodic table, the general properties, the detail, or rather, I should say, the important properties of the table, periodic properties, of course. So those properties will be discussed in a slightly more detailed way, considering some of the different perspectives of the elements and of the table. So based on that, we will be having our discussion, or rather today's discussion, on this, on these points, on these points. Now these points refer to the points which will be discussed in today's lecture. But before going or continuing with the lecture, I would like to highlight that there has been a logo given, if you want to check it out over there, which states two things. Well, first, it's written over there IYPT, which is a short form, and then over there on the top, it's written mention a year 2019, that means the last year. Along with that, you can see it's a global symbol which actually represents the international acclamation or acceptance of this periodic table, followed by the person who are responsible for this table. Now this IYPT is basically called as the International Year for Periodic Table, and the last year has been declared by the Scientific Forum as the International Year for Periodic Table. So it is basically celebrating the success and the international acclamation and acceptance of this table and the worldwide recognition of this table. All right. So let's move on to the periodic table straight away. We are having periodic properties, and over here we know that these properties, what I've been listed over here as the nuclear charge, atomic radius, ionization potential, electron affinity, electronegativity, all these things, all these properties we have already discussed. I shouldn't say discussed, rather, you must be knowing about these properties. Periodic properties, these are very important properties, and the variation of these properties along the period, down the group, or up the group, or so group-wise and period-wise analysis has already been done earlier. Then what else we are going to focus on this time? We are going to focus on much more, I should say, these properties in a more detailed manner. All right. So before proceeding to the details, I would like to recapitulate all these properties, which will actually help you all to remember if you have missed any of those points or forgotten any of those points. So as the following lectures will go on, it will be a help to all of you so that you can rather identify and correlate what these properties are and the upcoming details of the lectures. First, I'm going to go with the nuclear charge. To a very specific and precise way, it's the charge of the nucleus. Now, charge of the nucleus is a simple word but from where the charge comes from. It's exactly correct. That is basically the charge of the protons. We know that nucleus is having protons and neutrons, and neutrons are electrically neutral, and protons are electrically positive. They're positively charged species. So based on that, nucleus becomes positively charged center, and it is called as a focus, or rather explained, I should say, as nuclear charge. The second, we are going to atomic radius. Atomic radius is actually the distance from the center of an atom, where the nucleus is center of an atom means the nucleus actually. So from the center of an atom up till the valence shell. So that distance is called the atomic radius. Now that particular radius, we're aware of the fact that atomic radius depends upon the nuclear charge as well as the valence shell. So depending upon the nuclear charge, depending upon the valence shell, valence electrons, the atomic radius varies, period-wise, group-wise. Coming to the next, ionization potential. Ionization potential, we all know that it is basically the amount of energy required to remove an electron from the valence shell. And what will happen? It will be converted into a positively charged ion, or a positively charged species. So removing an electron will convert an atom, neutral atom, into a positively charged atom. Over there we have to supply energy, so that amount of energy is what we identify, what we refer to as ionization potential. The next, we are having electron affinity, which is actually more or less on an opposite of the ionization potential. Because in electron affinity, we actually gain energy. So it is basically the insertion of an electron to the valence shell of an atom, which results to the liberation of energy, which is referred, that energy which has been released is referred to as electron affinity. So previously in the ionization potential, it was giving energy, now we are gaining energy. Then moving on to electronegativity, that was basically, if you remember, the tendency of an atom to accept an electron. To accept an electron, yes. The tendency of an atom to accept an electron is what we call as electronegativity. So it's basically mere a tendency, how much an atom is prone to accept an electron, whether it's very highly prone or less prone, less susceptible. Okay. So today's our topic of discussion will be the size of an atom, and following these properties, or rather out of these properties, I definitely expect you to identify which property actually goes with size of an atom. So today our discussion is based on one of the periodic property, that is size of an atom. And size of an atom refers to, exactly, correct, atomic radius. So size of an atom refers to atomic radius. And why it's atomic radius? Because we know that atoms are spherical in shape, and spheres do have radius. They do not have length, breadth, height, they have radius. So depending upon the radius, the size of the sphere matters. If the radius is smaller, the sphere is small size. If the radius is big, the sphere is big size. So depending upon the size of the sphere, or rather radius, it actually governs the radius actually governs the size of an atom. We are now focusing on the definition of atomic radius. Though I have discussed earlier, but still I'm going to revisit that definition again based on with a proper diagram to explain. So it is the distance of the valence shell from the center of an atom, that is nucleus. So distance of the valence shell from the center of an atom, that is nucleus. So there shouldn't be any confusion regarding that. The nucleus, where the nucleus is. So nucleus is at the center and distance up till the valence shell. So this is how it looks like. You can check it out, the diagram over here. The nucleus at the center, from the center up to the valence shell, that's what we call as the atomic radius. Coming to the classification of the size of an atom. Classification. So we can classify. So classification of the size of an atom means we are actually classifying the atomic radius. Isn't it so? So we are actually classifying the atomic radius. What are the different types? Let's check it out. The first one is called a crystal radius. The second one is called a covalent radius. And what about the third one? The third one is called the van der Waals radius. So crystal radius, covalent radius, van der Waals radius. So these are the three major classifications of the size of an atom in terms of atomic radius. So actually atomic radius is basically, atomic radius is a general term. So atomic radius is actually classified as crystal radius, covalent radius, and van der Waals radius. We are going to analyze each and every radius individually. Okay? The first we are having the crystal radius. I every time say whenever we encounter a new word, we should go for the definition first to understand what the term means. We are having, it says that the half distance between the centers of two nuclei of two adjacent atoms in a metallic crystal, also termed as metallic radius. So we are having two atoms together, and within those atoms, if you check out the diagram, the representation of those two, the radius in the two atoms over there it goes. So we're having two adjacent atoms. That means they're remaining side by side, with their boundaries have just touched. So they're just at the closest proximity of each other. The closest proximity of each other where they actually meet at a point. There is a point of contact between the two atoms. Now that point of contact becomes slightly difficult to identify, and hence what is done? So the distance between the two nuclei is actually measured, and followed by the distance which has been measured. It's then divided into two equal halves, which gives the result that the distance from any of the nuclei up till the valence shell. So where the valence shell lies can be identified based on this particular crystal radius. Exact, rather more or less exact, I should say, the determination of the atomic radius of an atom. But consideration, the point is, it has to be a crystal radius. Now, regarding this, when we are considering a metallic crystal, this radius is also termed sometimes as metallic radius. Now, this sort of radius determination is done through X-ray diffractometry method. Okay. So now we are going to deal with covalent radius. So we have already discussed crystal radius. We will be doing now covalent radius. What is covalent radius? By the word itself, I think you can identify, you can have a slightly concept regarding it having some relationship with covalent bonds. And that's absolutely great. That's absolutely great. It is having a relationship with covalent bonds. How? It is basically half the distance between the centers of two nuclei of two similar atoms bonded by a single covalent bond. So it's basically half the distance, once again, half the distance between the centers of two nuclei of two similar atoms bonded by a single covalent bond. Now, there are certain important points within this definition. The first is the covalent bond. The second, two similar atoms. So these two are the primary, or rather important points when you are focusing on covalent radius. Half the distance, that's basically due to considered because identification of the boundary that where an atom ends. So that becomes a slightly difficult job, especially when uh, it is overlapping, there is a bond formation, or any sort of molecular interactions or any sort of atomic interactions. So figuring out the exact boundary of a particular atom, it's slightly quite difficult. So for that reason, to exactly measure where an atom ends regarding the atomic radius starting from the nucleus, that becomes a slightly problematic job. And hence, that distance between the two nuclei and dividing by 2, it's comparatively easy, and it gives a fair, correct result. So we are having the covalent radius with us with a diagram which represents that two atoms have overlapped and they are being under covalent bond. So they are sharing a bond between them, that's covalent bond. And due to that, the nucleus of the two atoms are actually having the closest distance between them. Now, after determining the distance between them, they're actually divided by 2. That means they're actually halved. And the distance of those calculated, that means the half distance, is what we call as the covalent radius. Now, this distance are again resolved by using X-ray diffraction technique. So X-ray diffractometry or X-ray diffraction technique, this method is generally always used. The second thing is, these distances are additive in nature. That means, especially required for heteronuclear molecules. So when we are interested that what is the molecular size of a heteronuclear molecule? Heteronuclear molecule means, hetero means different. So a molecule containing two different atoms is actually referred to as the heteronuclear molecule. Okay, so for heteronuclear molecules, this covalent radius is very important because from individual covalent radius calculation and identification, that means for similar atoms, that particular data, that those atomic radius, that can be used to add up, rather to, I should say, that can be used in different molecules where different atoms are present, or whether the values are being added up, we will be able to get the corresponding size of the molecule. For that reason is said, it is additive. So just we need to add them and we will get the size. Now the radius of the two separate atoms will be added up to give the internuclear distances. That's it, simple. Okay. Moving on to van der Waals radius. Now, van der Waals radius is once again half the distance between the center of the two nuclei, but of the same substance, the point of interest, the important point, that is at the closest approach. Now, what does this mean? It's highlighted over there. What does this mean actually? If you look at the diagram over here, we're having two atoms with a center having a nucleus, and the distance between them, then the distance is actually divided into two equal halves, and that's what you call as the van der Waals radius. Now, this van der Waals radius is not dealing with exactly the atomic radius. So it is slightly more. So van der Waals radius of an atom is determined, but van der Waals radius is slightly greater than the normal atomic radius determined of an atom, because it is basically outside the boundary of an atom. It is basically considered as an outside the boundary of an atom. So based on that reason, it is the values of van der Waals radius is slightly more. Okay. Now, what is this closest approaches? This is basically when two atoms are coming close to each other, but they will not form a bond. They will not share in relationship. The relationship is basically they will have an influence of one over other. They will have an influence of one over another, but they will not, I repeat, they will not be able to make any sort of bond between them. So they will just have an influence, They will be at their minimum, rather the maximum closest distance as possible without forming any bond. That's we call as the closest approach. And there is a significance of the van der Waals radius and the van der Waals force also. Once again, X-ray diffractometric method is of determination, but there are other importances also. Now, regarding when we are discussing about the points of interest and other van der Waals radius, it is basically considered important for when it is focusing on dipole-dipole interactions. Okay. It's basically forming a dipole-dipole interactions with intermolecular forces. So these terms include the intermolecular van der Waals radius, closest approach. It's basically considered as dipole-dipole interactions. So when there is a dipole-dipole interaction, one atom is over having an influence over the other atom. So what is the minimum distance without forming any bonds? So they will have interactions, but they will not form a bond. So they will not change their properties, and hence it's called it's referred to as the van der Waals radius. It's very important in determining how the molecules are packed within solids. That's a very important relationship. So these are the three radius in simple, explaining them in simple terms. Now coming to another parameter, that is what we call as atomic volume. What is atomic volume? Atomic volume is basically the volume occupied by 1 gram atom of an element at standard temperature. So the volume occupied by 1 gram atom of an element at standard temperature. So we are very much familiar what is standard temperature and pressure. So we know what standard temperature is. That's the point which should be noticed over here. That is 1 gram atom of an element. The question obviously arises, what is 1 gram atom? Now, I can expect that many of you must be knowing that what is gram atom is. Gram atom is actually the number of atoms present in a molecule of an element at standard temperature. So it is basically the number of atoms. 1 gram atom is basically referred to as the number of atoms present in a molecule. I shouldn't say only one molecule. Better to say, specifically it is 1 mole of a substance. So the number of atoms present in 1 mole of a substance, here is element. So let's go with element only. That means 1 mole of a substance within, and 1 mole, the number of atoms in 1 mole of a substance here is elements at standard temperature. So this is what we call as atomic volume. The atomic volume, I hope it's clear. Simple number of atoms in 1 mole of an element. That is atomic volume. We would like to express that for alkyl metals, they are having the maximum volume, while the transition metals, they were having the lower volume. Very, very less volume compared to the other metals. So alkyl metals are having the maximum volume, while the transition metals are having a lower volume with respect to other metals or elements. Now, when we were continuing our discussion with atomic volume, a certain question arises: what should be the trend of volume without any other influence over the volume? What should be the trend of volume without any other influences over the volume? Obvious question. So, simple, down the group, it should increase, and along the period from left to right, it decreases. Now, though it has been said that it increases down the group and it decreases from left to right of the period, but what is the basis of this? What is the basis of this statement? There should be some basis of this particular conclusion, that this is increasing down the group and decreasing along the period from left to right. The reason is, over here, the volume has been considered calculation. I should say, as 4 by 3 pi r cube. So it is actually not the atomic volume in simple, it is basically as the volume of one atom. Volume of one atom. So just considering as r equals to the radius, normal radius of an atom. So we, considering the radius of an atom as general r, so we can calculate the volume of one atom. Based on the volume of one atom, we can obviously calculate the volume of 1 mole of atoms of an element. We can calculate. If we can calculate the volume of one atom, considering the radius, general radius as general radius only, without any sort of classifications or any specific radius, then with volume of one atom, from the volume of one atom, we can calculate the volume of 1 mole of an atom, 1 mole of, rather I should say, the volume of the atoms present in 1 mole of the substance. That is also can be calculated, 1 mole of the substance. And hence, from that, we will get the atomic volume. Now, after calculating the atomic volume in a general way, that is, by generalizing the atomic radius without any other classifications, if we now reproduce the atomic volume in a different way means we are going to present atomic volume in terms of the different radius. Not going to generalize the radius as an atomic radius only, but we are going to represent atomic volume in terms of covalent radius. That means atomic volume will be represented in terms of crystal radius, covalent radius, and van der Waals radius. Then what will be the scenario? But for knowing that scenario, we need to understand the scenario of the individual radiuses first. So we need to understand the radii scenario first. Based on that only we can predict, we can conclude that how the atomic volume scenario will be. Let's arrange the radius first, all the radii. So we are going to go with in terms of ascending order. Okay, we are going to go with in terms of ascending order. The smallest ascending order, so the smallest of the radii radius is covalent radius. Since they are having a covalent bond, so that the two nuclei, they are the closest to each other, and hence they are called the covalent radius. They are actually the smallest one, followed by the crystal radius that we have seen. The crystal radius, the distance are slightly bigger. They are having the nuclei distances are slightly greater compared to the nuclei of the covalent radius. And the third, we are having the van der Waals radius, where nuclei are farthest from each other. So if we look at this trend, what we can conclude that the covalent radii is less than the crystal radii, and the crystal radii is less than the van der Waals radii. Right? Now, if we just substitute these values into calculating the atomic volume, then what will happen? What will be the trend? Now, in respect to the analysis that what we were considering, that substituting the values, what's result is analysis on the basis of these three radii reveals that the variability in the volume of an atom is expected to follow the same trend as is shown by the different atomic radii if arranged in ascending order. What does this mean? This means that if we consider the trend, that is the covalent radii is the smallest one, crystal radius at the mid, and the largest is the van der Waals radius, then if we substitute these values individually in calculating the volume of one atom, just volume of one atom, then the output will be, the result will also represent the same trend. That is, the volume of one atom, by considering the covalent radii, will be the least, and the volume of one atom, by considering the van der Waals radii, will be the largest, the maximum. Now, if this is the trend, then of course the atomic volume, that means if we follow the definition as it was stated, that is the volume or of 1 gram atom. What is one gram atom? Number of atoms in 1 mole of an element. So if we know the volume of one atom, then we can calculate the volume of the total number of atoms present in 1 mole of a substance. And that will also represent the same trend following the covalent radius, van der Waals radius, or the crystal radius, the metallic radius, the same trend. Hence, if we follow this trend, if we follow this particular trend, definitely we are going to observe that the volume calculated by using the covalent radius is less or the least, which is lesser than volume calculated by using crystal radius, which is lesser than volume calculated by van der Waals radius. This trend is obviously expected. What is the conclusion regarding this? The conclusion is the electrons within a molecule formed to covalent bonding are having the least distance, definitely. If the nuclei are having the least distance between them, then definitely electrons will also be having the least distance between them. And since why this is the thing? Because electrons are actually responsible for any sort of bond. Any sort of bond formation, electrons are only responsible. And thus, we can conclude that electrons within the molecule formed due to covalent bonding are having the least distance between them in comparison to the electrons of the other two bonds. Though over there it said that van der Waals radii is no bonds is being formed, but still there's a force of attraction, there's an influence is going over there, and for that reason it's a van der Waals force and van der Waals interaction, you can say. Sometimes it's also referred to as van der Waals bond, but very least but van der Waals force of interaction. I followed the previous one as metallic radii. The metallic radii is sometimes considered to be as metallic bonds also. So in comparison to the other two, the electrons for the covalent bonds are having the least distance. That's the conclusion. So the same trend goes on. Volume, our covalent bonds, or covalent radii having the least volume, followed by the crystal radii volume, less than, and which is lesser than the van der Waals radii volume. Now from here, a very important question which arises. A very prominent question, a very significant question. What's that? The question is, what is the trend of this radii within the periodic table? Isn't it so? We're talking about periodic properties, we're focusing on atomic radius. We have classified the radii into 3 different radii: crystal radii, covalent radii, or rather you should say from ascending outwards, covalent radii, crystal radii, van der Waals radii. All these things we have classified. We have discussed atomic radius in our earlier classes, so we have read about that. And atomic radii is having a trend along the period and along our period-wise and group-wise. Then what about these radii? What's the trend? The answer to this question will be given in the next upcoming video. So for that, to be continued, of course. So I'll conclude my lecture today up to this much. We'll catch you up with our answer to this particular question in our next video. Until then, thank you so much. Stay safe. Take a very good care of yourself. God bless you. Thank you.